Hi everyone, the time is 2:50 p.m. and we are going to start class at 3 o'clock. So if you're watching this video in retrospect, you'll want to fast forward about, well, now it's 51, so about 9 or so minutes. Yeah. Meeting. All right. Hello, for those of you guys who are here. So the time is 2:56, and we are going to be starting in about 4 minutes. Let's see here. A couple things I got to get situated on my computer. So how are you guys doing today? How's everyone doing out there? Sleepy, pretty good. I think I can identify with most of those. There's one other thing I need to grab to get ready for. What is that? So I don't have it. All right. Yeah, nice sunny weather outside indeed. We've been so fortunate, just like the past few, couple weeks, really. It's been just glorious outside. Makes me happy, you know. I know that I'm somewhat stuck inside, but it just makes things a little less of a downer if there's sunlight. I don't know. Do you guys feel the same? Yeah, it's definitely nice, going for, I feel like I can at least go for a walk outside, and around the neighborhood or something, even if, can't really go places, at least I can, go for a walk outside and it's not rainy and nasty, right? Yeah, I agree. Easier to stay optimistic with blue skies and cheerful birds outside. Oh, if someone's training their dog, yeah, for sure. Now I can't remember where I heard this, but someone was saying that now is actually an excellent time to get a new pet because pet owners are now home much more frequently, provided that you're not an essential worker who needs to go in, and that you have more time to spend training your new animals if you get a new animal. So let's see, it is 3:00, so let's go ahead and get started. I wanted to start today by saying a huge thank you to any of my students who are essential workers and who are going into work and risking being exposed to the virus that's going around. Really appreciate you guys, and a special shout out to anybody who may be listening who's a healthcare worker, whether you're a technician or a nurse or anything else. Thank you so much for doing what you're doing during this time. I know that myself and others really, really appreciate everything that you guys are putting on the line for your jobs, for work, to help other people during this time. And even if you are working an essential job, whether that's like grocery store or delivery truck or something, thank you so much for, doing what you guys are doing during this time. It's not easy. It's not easy for anybody, for those who are out of work or who are working from home or who have to go in and work and be in contact with other people. So thanks for what you guys are doing out there. So with that being said, something else that I wanted to just mention before we get into lecture today, I saw in a memo in my email that there are 3 scholarships being offered by East County campus. And they are $800 each scholarship, $800. And the deadline to apply for that is May 1st. I'll put the link in an announcement on Canvas so that you guys can check that out and check the details and see if that's something that you want to apply for. This colorful map behind me, hopefully I can make it look a little bit prettier next week. It is, you might be wondering why this map of the United States has all these weird, crazy colors on it. This is actually a geologic map. It's not showing the different rock types. However, it is color-coded by the age of the different rocks that are exposed at the Earth's surface. And there's a key over here on the side showing the lighter yellows at the top are more recent time, and then all the way down here to the red, those are the oldest rocks that are depicted on this map. So Washington's kind of folded over. Sorry, guys. But yeah, so this is kind of like what geologic maps tend to look like. So just kind of a random tidbit. So today we're going to be talking about the scientific method and minerals as well. So let's see what we've got going here. So if you guys have this diagram here, it's on Canvas. If you guys could pull that up, that'd be great, because we're going to be talking about this today, the flow of the scientific method and how does one do science? Have you ever wondered, like, what qualifies as science? Adam Savage on Mythbusters says that the only difference between science and goofing around is that you write everything down. And that's somewhat true. That's definitely a big part of it. However, there are a few steps that are also really important for something being considered, doing something, doing it the science way. So let's see where my cloth is here for whiteboard. All right, so how does one do science? The first step in conducting science is you're going to want to make an observation. So for your observation, you might just observe some sort of phenomenon that's going on around you, right? So say you observe, I like to use an example. I'll go with, for a while I was babysitting my niece. She just turned 4, holy cow. But when she was an infant, I was babysitting my niece several days out of the week. And she would cry from time to time, as infants do, right? So my observation might be, in that instance, that my niece is crying. That would be my observation. And we can do science around this, right? So after you do the next step after you make your observation, next, what you're going to want to do is form a hypothesis about that. I also want to point out that these words are absolutely extremely important. Using the actual like vocabulary of like observation, hypothesis, etc. Those are, it's really important that you actually use the term hypothesis and not like, theory, etc., because that has, these words have very specific definitions in terms of science, rather than when people are just kind of using them kind of colloquially. So a hypothesis is going to be an idea that you have, right, about the observation that you've made. So going with the example of my niece crying, I might say, well, my hypothesis is that perhaps she's hungry, right? So the next step after forming a hypothesis is to devise a test by which you can test your hypothesis and determine whether your hypothesis was correct or not. So for me, with my niece, my test might be to grab a bottle full of milk, formula, whatever, and see if she wants to take her bottle, right? She may not be hungry though. So the next step after you conduct your test is you're going to either get kind of an indicator one way or another. If my niece doesn't take the bottle, right, she pushes it away or something like that, I might consider going back and revising my hypothesis. And perhaps that wasn't it. Maybe that's not why she's crying. And maybe I didn't hit the nail on the head. Perhaps there's a different reason. Perhaps the other reason is less favorable. So it's important to go back, change our hypothesis at this point, right? And then we're going to devise a new test. So my new hypothesis might be the least favorable one, that she has needs a diaper change. So my next test would be either to sniff her diaper or to maybe actually just change it, as I frequently would, is I'd just be like, I'm just going to change it, whatever. And just change her diaper and see if that's what she was needing and why she was crying. If that ends up not being the reason why she's crying either, we have to go back yet again and come up with a new hypothesis for why she's crying. And once we have our new hypothesis, my new hypothesis is going to be that maybe she just wants to be held, because that was sometimes the case, that she just was bored and wanted to be picked up. So that might be my next hypothesis, is that she's just, wants to be held and wants to be picked up. So I would test that by picking her up and holding her and seeing if that's, what she wants. And perhaps that's not the reason either. Perhaps she just needs a nap. Could do this all day. So once you get a reason, though, once you get kind of something that indicates your hypothesis was correct, right? You don't have to keep going back to the drawing board and revising your hypothesis. So say I recognize that she wants to, say it was that she had a stinky diaper, right? I can eventually realize that becomes like a theory. So in science, if you test a hypothesis, right, and it stands the test of time and multiple tests, your hypothesis gets upgraded and it becomes what we call a theory, right? You know, some parents and their kids, like, they even develop, like, they're able to tell what kind of cry their child has, and they can tell by the type of cry that it's like a stinky diaper, or that it's, you know, I'm hungry cry, or I just want to be picked up cry. And in those cases, they've, you know, they've arrived at the theory state for the various, like, cries that their child has. I don't know that all children have, like, a specific cry or whatever, but some parents, like, they swear it's like, no, they really do have a different cry, and maybe they do. So it's important at this step, though, even once you have a theory, you're not done yet. You're still not done doing science. You're going to need to continue to go back. Whoop. I've left the cap off my purple pen for too long. See if I can bring it back to life. Not really. Let's go with a black pen. So you're not done yet doing science at this point. You still have to go back. Not that far. Not yet. And you need to devise more tests, right? I think I'll actually draw it a different way, more closer to the handout that you guys have. I like that. So you're going to have to continue. Am I still in frame? I am. Conducting tests, right? I mean, sometimes, you know, we get it wrong. We don't know our infant's cries well enough, and we're just like, you know, so you keep testing that as, you know, life goes on. And sometimes you realize that you may have been wrong, like, just altogether. Maybe you were off the whole time after doing, and you repeat this, you know, various tests and whatnot, and come up with new tests. And if you realize you were wrong the whole time, you have to go all the way back to the hypothesis step and formulate a new hypothesis. At that point, it won't have graduated to theory because it's a new hypothesis. It's a new idea. And then you go through the testing, right? Devise new tests and repeat those tests. And eventually, after refining your hypothesis and passing more and more tests, your hypothesis will yet again graduate. Your new hypothesis will graduate to a theory, and you continue to conduct tests even at that point. And if at this stage you start really passing a lot of tests and you have pretty good support for your idea, you can eventually graduate yet again. Am I still in frame? I hope so. Sorry, my writing's a little bit crooked there. It's difficult writing sideways. Your theory, your idea can graduate from theory to a law, right? We're still not done yet, though. Even after something has become a law, you still need to do more tests. Right? Wow, that is so crooked. So sorry, guys. So you still need to do more tests. And it is possible that even at this point of testing, the reason why this is so important, let's try and make that at least semi-straight for you guys. It's a little bit better. So even at this point, though, it does happen that laws, you know, they get overturned, right? And you may have to, if it doesn't pass, you may have to go all the way back. Let's get a little arrow there. You may have to go all the way back and formulate a new idea that will be a hypothesis because it hasn't graduated yet. Let's see. Another theory could be needing to be lulled to sleep. Yeah, so And theory is nothing to scoff at if you're in the theory step. For example, we call things like the theory of evolution, the theory of plate tectonics. law is a really hard status to achieve. Like, we have the laws of motion. Those have been, that Newton came up with. Those have stood quite the test of time, and it's important to continue to test them because someday some quantum physicist is probably going to come along and probably tell us that we've been wrong the whole time. So it's important to continue testing things even at the law stage. And it's really difficult to graduate all the way to law. So when you have something that says theory, right, know that it's kind of here in this stage, but even that stage, that's hard to get to. So this is how one does science. So can you guys think of maybe any other ways that you might do science in your day-to-day life, perhaps? We really do this a lot, an awful lot in day-to-day life. And we just don't think of it as science, but it really is. I also want to be careful too that with the idea that some things get considered science because, it's been kind of like anecdotal, right? You really do need to be recording stuff down. And your tests that you formulate need to not only be anecdotal, just this was my experience. It also your test needs to be repeatable. Someone else needs to come along and be able to conduct the test the exact same way. So in that regard, my niece crying is a pretty good example, but it's not like the best example because I can't I can repeat the test, but she's going to be crying. I can't go back in time, and test her like re-crying or whatever. Let's see what we have in the chat. Someone says with cooking. Yes, that's one of my other favorite examples is like with cooking, especially like baking. And then Alicia says explaining those bizarre noises coming from beneath the hood of the truck. Yes, absolutely. Right. And someone says, Michaela says, anytime I take on a new houseplant. Yeah, I just recently started getting into houseplants this last year. And let's see, we have experiencing a different food combination, creating new recipes. Absolutely. When I first taught myself computer programming, used the scientific method repeatedly. Absolutely. I did a tiny bit of coding this summer, learned a bit of that I sat in on one of our engineering classes on campus, and boy, yeah, kudos to you, Brendan, because that's hard stuff, and I barely got the hang of it. I only didn't, just barely the beginnings, got the hang of it. Not really. Yeah, you use the scientific method a lot there, absolutely. Over and over and over again. So this is extremely important. I can't tell you how many times it bothers me when people say like, oh, but there's science behind this. But in order to qualify as science, you really do need to be following this procedure. And not only do you need to be following this procedure, it has to be recorded and it has to be retestable, right? And if you're testing something that involves like a human element, right, you need to be able to have large enough sample sizes, right, in order to be like statistically significant. And if it's something like baking, you may want to do enough trials, right, so that you have a statistic significance, right? You may need to do the same test enough times to prove that it wasn't just a fluke, right? The first time or the second time even. You need to have enough tests to really, hit that nail in the coffin, So also painting, art in general, yeah. Let's see. Hardest part of conducting coding is controlling all the environmental variables. Yeah, absolutely. So this is the scientific method. Does anyone have any questions? If you do, go ahead and put them in the chat. And with that, that kind of wraps up our scientific method talk. This is, while it is just a really short topic, it is something that you guys will want to know. It will be on the tests and such. So this is something very important to dedicate. And it's also really important to know, because then when people come to you and say things, try to sell you something, and they say that there's like a lot of science behind it, you can like come back to this and be like, well, did they do multiple tests, enough tests that test the same thing enough times to be statistically significant? And is that test repeatable? Can I do it myself? Can I go back and read up what they did and repeat it? So clinical trials may improve laws of physics, absolutely. Clinical trials have to have enough people in order to be like statistically significant and stuff and whatnot. So, and your test has to be repeatable. So you need to have recorded it in enough detail that someone can do the exact same thing, controlling for as many factors as possible. So like with your oven, like if you're baking, you might even go so far as to measure the internal temperature of your oven to make sure that if you have a digital display, you know, that whatever, or a turn dial, that it's actually at like 400 degrees Fahrenheit, right? And not a little bit off. You might even go that far, so that way someone can, you know, assuredly repeat it. And you would want to write that down. I actually tested my oven temperature, and it is indeed 400 degrees Celsius, or not Celsius, good grief, Fahrenheit. So as seen on TV, as seen on TV, not my favorite things, right? So let's go ahead then, and it doesn't appear like there's any questions. In the next week, a little bit of homework that you don't have to turn in. In the next week, definitely be thinking of ways that you use the scientific method in your own personal life every day. Maybe you guys, it would be cool if any of you guys decide to, you guys are presented with something throughout the next week and you just say, aha, how can I approach this using the scientific method? Give that a try this next week, okay? So that is the scientific method. And again, this diagram is on Canvas. It was previously in the plate tectonics module because I usually like to go over this the first week, but in doing plate tectonics for the first week this time around, there's just so much content there that I really wanted to move this into a different week. So normally we would do for this activity, for the scientific method, I have an activity where I have some mystery boxes that I give to students and a worksheet, and your job is to determine what you believe, what your idea of what's inside the box, and go through various tests, forming your hypothesis, testing it, and then going back to the drawing board if your test seemed to lead you in a different direction. The catch is that you don't get to open the mystery boxes at the end of the activity, and that really gets a lot of people's goat. So, sorry guys. All right, so I was unable to get the PowerPoint to print. I even had a hard time uploading it to Canvas because the PowerPoint has, I think, just too many pictures per slide. So there's a link on Canvas to the Google Slides where I made the PowerPoint, and you guys can follow the link to there, or you guys can also like download it from there and print it if you guys are able to get your printer to handle the PowerPoint. So go ahead and pull that up if you guys are able to, or if you have a printout in hand, go ahead and grab that. Also we need to talk about like your rock kits and stuff, because a number of you guys have the rock kits. There's a few of you guys though who haven't received yours yet. And I understand that with the virus going around that things may be delayed in in shipping these out to you guys, or as well as just general shipping, getting things in the mail may be delayed. But fear not, our week's activities can be conducted without your rock kits. These ideas just become a bit more abstract if you don't actually have something in your hand that you can look at while I'm telling you about various mineral properties. But it's okay. We can still get, we can still make it without it. Have faith. This week's lab is just going to primarily be filling out a chart. Normally, I would have you guys identify your minerals. However, the kits, I believe, come with a key. At least it says online that they come with a key as to what samples are which samples. So the mystery is gone. I can't make you guys just randomly identify your samples. And then on that chart that I've provided you guys with on Canvas to fill out, there are a few samples that have an asterisk next to them. And those samples, I do want you guys to make a sketch of and submit a sketch of those samples as well. I believe that all but 2 of those samples are in your rock kits. So for the 2 that aren't, or if you do not have your rock kits yet, you can just find a picture online and sketch that. It's definitely not ideal to do that. It's strong preference for actually grabbing a sample if you have one and observing your own sample and really seeing as you move it, in front of you and it reflects light back at you, you're going to be able to understand a lot more of what you're looking at as opposed to a still picture. So let's see, we'll go over the samples in your kits like more in depth on Wednesday. And hopefully some of you guys are able to receive your kits between now and then. But for today, let's go ahead and talk about the various mineral properties and talk about minerals in general. And I have a lot of my own samples here that I can show you guys, as well as some kind of household objects that really exemplify the properties that we are talking about. So first, let's go ahead and go over a geologist's definition of what a mineral is. What is required in order for something to be considered a mineral, right? So first of all, it has to be, let's see, did I skip? I feel like I skipped a slide. I did. Hold on. First, we need to talk about why they are important. I usually like to go over at least a little bit of information for why is this, why am I learning about minerals? Why am I learning about this geology stuff? I like to give you guys at least a bit of a frame of context. So the second slide on that PowerPoint is a picture of a bunch of random objects. We've got like cell phones on there. We have makeup and dishes, right? There's some salt and a car and some coins. So the reason why we want to learn about minerals, why we should care about minerals, just, as, random people who maybe aren't geology majors, is because your life does, again, depend on these minerals. Almost all the objects that you use in your day-to-day life have minerals in them, or maybe completely minerals. So some of you guys might be writing with one of these today. It's a pencil. And the lead in your pencil is not lead, thank goodness. Used to be lead. They actually used to use real lead. That's also a mineral. But lead's dangerous for you, so they stopped using lead. And they moved to a different mineral called graphite. If you have the larger kits, I'm pretty sure that there's a sample of graphite in the larger kits, a nice big chunk of it. You can tell because you can write with it. And they don't, to my knowledge, do anything with the graphite in pencils to like alter it at all. It really is just graphite. And it's a very soft mineral, right? It is kind of metallic looking, but it's so soft that you're able to just transfer it to a piece of paper just by applying, a slight pressure. So it's important for people to care about minerals because we do use them. You use them in your cell phones, right? Or other electronics, whether it's like copper in the electronic or like quartz making like silicon wafers, or like coltan in resistors and capacitors and stuff. Makeup, if you've ever wondered what the like little sparkly things in makeup are, not like glitter, but just, those kind of reflect sparkle things in your makeup. Usually it's the mineral muscovite, and you actually have a sample of this in your kit. It is sample number 3. If you have the larger kit, like I do, because that's the only one that we had on campus was the larger one, it would be sample number 4 for you guys. So this thing is, they grind this up into little tiny bits, and those are the sparkles in your makeup. And even dishes are also made out of minerals. I believe it's typically like feldspars and coins, obviously. I hope you guys were able to track down a copper penny 1982 or older, as well as other metals. A lot of metals, if it's not an alloy, are going to be native minerals as well. So salt is actually a mineral too. It's edible. You can eat it. The mineral name for salt is halite. We don't actually call it salt in geology. Sometimes you get pink Himalayan salt, and that's like the fancy stuff, right? So lots of applications for minerals. All right, moving on to the next slide. Let's define a mineral. What makes something qualify as a mineral? Does a tree qualify as a mineral? No. Why not? Because we have a strict definitions. So it must be naturally occurring, right? In order to be considered a mineral. It must be found in nature. There are minerals and things that we have made and created in labs, but we haven't been able to find them in nature. And for that reason, we can't truly call it a mineral. So another thing is that it needs to be inorganic, an inorganic solid, right? So we're not talking about things like trees and plants, which are made of organic material. We're talking about inorganic stuff that's naturally occurring. And in addition to that, it needs to have an orderly crystalline structure. So now we're talking about chemistry, and on a molecular level, we need to have an orderly crystalline structure to it in order to be considered a mineral, right? So it can't be just all over the place. It's got to have that nice, we'll look at on some later slides, some pictures of kind of that molecular structure. We might go over that more on Wednesday though. So in addition to having naturally occurring inorganic solid, orderly crystalline structure, it needs to have a definite chemical composition as well. So it has to have, you know, a definite, you can add like accessory elements onto that chemical composition and things like that, or like swap out sometimes like certain things, and that becomes like okay, and it just changes the color of your mineral a little bit. Is it pronounced crystalline or crystalline? I have heard both. I say crystalline, not crystalline, but I don't really know that it's wrong to say crystalline. I would just phonetically, it looks like crystalline to me. I think that it probably has to do with whether or not you have an accent, and I think that in a British accent that they pronounce their I's a little bit differently, and I think that might be where that comes from. Not sure though. It's not wrong if you say crystalline though. It's not in my opinion. So let's also move on then to the next slide. Celtic or Celtic? I don't know. Celtic or Celtic, potato. Let's move on to that next slide. There's this beautiful piece of granite on there, and it's a true granite. You've got that salt and pepper, you know, white and black, and then you also have some pink in there. And in my opinion, true granite's got to have a little bit of pink in there, because that's a specific mineral that's really important to qualifying a rock as granite. We'll go over more of that stuff later. So it says building blocks of rocks. And what is meant by that statement, building blocks of rocks? What is meant by that statement is that a rock, right? I have a shelf here full of rocks. I think it's one of my favorite shelves in the house. My other favorite shelves also have rocks on them. So a rock is an aggregate of minerals. So it's a bunch of minerals stuck together, right? In one big giant thing. So here you can see kind of like I've got this section right here. There's some black, really dark dots in there, right? That's tourmaline variety squirrel. I don't know how to say it. Someone can correct me. I'll look it up later, probably. Maybe. I might play Animal Crossing instead of looking it up later. And then right here, this really sparkly, really shiny area here, and you can see it kind of all throughout. That is also muscovite mica in there. Here, this kind of white spot is a feldspar. It's probably potassium feldspar. And then this kind of like brownish, smoky kind of thing is some quartz right in there. So this is considered a rock because it's a whole bunch of minerals that are all smushed together into this thing. Sometimes for rocks, you can't see the individual minerals with your naked eye. This is pegmatite, by the way, for those who are a bit more advanced and are curious about stuff like that. Sometimes it's, you know, the minerals are really like fine grained and you can't see them with the naked eye. And for sometimes we will use like a hand lens to help us see the individual mineral grains. However, there are still yet times where even with a hand lens, a magnifying glass, some people call that a jeweler's loupe, there are still yet times when even then you can't see the individual crystal grains, like this rock that I've got here. This is a volcanic rock. And for that, you might need a thin section to see the individual crystal grains. However, you should still be able to see the individual crystal grains. So minerals are the building blocks of rocks. It's the stuff that rocks are made out of, right? And in order to be considered a rock, it's got to be an aggregate of several of these. So have you ever wondered, what exactly defines a rock? It's an aggregate of minerals. So that's what's meant by the statement that they're the building blocks of rocks. So in that picture there with the granite, you can see that they've got a sample of quartz there, and it's kind of pointing to the areas in that granite where you can see the quartz. In the granite, they're kind of like this grayish, smoky kind of colored mineral. The reason is because light's not really passing through it. It probably would be a lot lighter in color if we were to pluck out those individual quartz grains, but they're in shadow from all of the other minerals around them. And then it also says hornblende. That's another mineral. All three of these minerals are in your kits, by the way. Hornblende, another mineral in there. That's the black stuff that's in there, most of the black stuff. And then feldspar, this other kind of pink mineral there. That's specifically potassium feldspar, or K-spar, colloquially we call it. And that's the pink stuff that's in there, right? So in that granite that you have there, it's very clearly depicted. You can see the different individual minerals that are making up that rock. So let's go ahead and move on to the next slide, right? It's got some pictures at the bottom. It's got a picture of gold in quartz. Beautiful stuff, beautiful. There's also a picture of sulfur at the bottom and a picture of copper as well. So most minerals are chemical compounds, meaning that there are several elements in the compounds that make up that mineral. So quartz's chemical formula is SiO2, right? Some of you guys are familiar with water, H2O. Here's an interesting thing. Ice is actually a mineral. At least according to my mineralogy textbook from college, they actually do list, ice is actually a listing in there. And my favorite little Easter egg that was in that book was that in the definition of there, it had all this, fancy science stuff written out. And then at the very end of it said, and like economical uses. And at the very end, it was like, it's also used to parch, or it's also used to help quench the thirst of parched geologists and stuff like that, and cool their beverages. I thought that was funny. Kudos to the authors for including that little Easter egg in there. So most minerals are made up of several elements, right? H2O, in the case of quartz, Si, silicon, O2, oxygen, two oxygen atoms, I believe. Chemistry is not my thing. Yeah, chemistry and I aren't friends. I used to think that like math was my worst enemy. And then I got into college and met chemistry. And I found out that I had a greater adversary. Let's see. So, however, there are a few minerals, though, that aren't chemical compounds where you have more than one element in there. Some minerals are actually just a single element, and we call these native minerals. So, for example, copper. Copper is an element on the periodic table. It does occur in nature, though, on its own, just straight copper. Same thing with like gold and sulfur as well. So I have an example here of copper that I'll show you guys. You can take a look at your pennies, right, as well. If you guys happen to have that, that is pure copper. Oops, sorry, dropped that on my laptop. I also have some native copper here as well, that's found in nature, right? Let's take a look at that guy there. So it kind of forms in like this weird structure. The bluish greenish stuff, ignore that. That's something else. It's another mineral. We won't talk about it though. The silver or the coppery colored stuff though is indeed, you guessed it, copper. So that's what a native mineral is. It's something it's naturally occurring in nature, and it's not a chemical compound. It's made of just one of the elements on the periodic table instead of two or more. So the next picture on that slide is just for fun. It's a super cool, I think there might actually be 2 slides dedicated to it. I'm looking at a different PowerPoint than you guys are. There's some pictures of the Crystal Cave in Mexico. This cave is just so awesome, and it's one of the reasons why I love minerals, is that minerals just can keep growing. They can just keep getting bigger and bigger. So much so that scientists' minds were blown. Crystalline, yeah. That scientists' minds were blown when we found this cave in Mexico that had gypsum crystals that were the size of evergreen tree trunks. And you can see, looking in those 2 photos I believe you guys have, the people in there are just tiny. And they're standing on these crystals that are the size of tree trunks, big trees. And there is a link too on one of those slides to a little YouTube video, short video, 4 minutes, I think, about the Crystal Cave in Mexico. It's a really weird place on Earth. You can see that in one of those 2 photos, there's a guy in an orange suit. And you might be kind of curious about that. He's in a suit because that cave is so hot. It's deep underground, and it's so hot that you have to wear a special air-conditioned suit to be able to stay in there for more than 10 or 10 minutes without dying. So super cool place. Again, those crystals are solid gypsum. So check out that link to learn more about the Crystal Caves. Let's see. Next slide that you guys should have is talking about the economic value of minerals, right? So again, we mentioned that minerals are important because they're in the objects that we use every day. And that means that these are economic uses. These minerals have economic importance. So you see some copper wires at the bottom, a thing of toothpaste. We also have, again, the example of graphite or pencils and stuff. Those are just some examples of economic uses. What's in your toothpaste? What's in your toothpaste? It's a mineral. It's called fluorite. If you happen to have the larger rock kit, the 50-piece rock kit, there should be a sample of fluorite in there. Copper wiring, so a few economically important minerals are going to be things like some of your sulfide minerals. There are different classes of minerals. So things like galena and sphalerite, right? And some native elements. We've got things like gold and copper, silver, right? Fluorite, again, it's in your toothpaste, right? Quartz gets a variety of uses. And then the mineral corundum, spoiler alert, the mineral corundum is actually the mineral name for the gemstones ruby and sapphire. I definitely hate gemstone names because they're not based on science. They're based on things like color, but it's really the same thing. It's just a slightly different color. So there's corundum, right? And there's all kinds of minerals, again, that are very economically important. One of the columns in the chart that you guys are going to be filling out for your lab is actually dedicated to you guys learning, finding, researching some of the economic uses for those minerals. Let's see here. Going on, let me pull up Hold on one second. Pull up another slide here. All right. Realized that the PowerPoint I was looking at differed kind of slightly, and then was like, wait a second, I had other slides that were inserted into here for you guys. So let's talk about crystal habit and crystal shape. So now what we're going to be transitioning into are the physical properties that we as geologists use to identify a mineral. So if I come across a mineral out in the field while I'm doing research and I need to identify it, there are several physical properties that we use to determine which mineral it is. And if we were actually having like an in-person class, I would give you guys a kit of unlabeled samples. They have numbers on them and that's it. And I won't tell you what they are. And you just go through and you use all the physical properties to conduct all of your tests to determine which mineral it is. But spoiler, I actually am going to have you guys do that because one of your samples in your kit, sample number 2, is just labeled feldspar. Feldspar is not a mineral. Feldspar is a family of minerals. So just like your 2 minerals that say mica muscovite and mica biotite, mica is not the name of a mineral. It is the name of a family. It's an umbrella term for several minerals that fall within that family. And so you guys were blessed with a sample in these kits that just says feldspar, but that is, just the family. So I'm going to have you guys identify which feldspar you guys think it is. I gave you 2 options for which feldspar it might be. So you guys will actually be identifying that one. It says on the chart when you pull that up, in the second space, it says feldspar, and then it says right here in parentheses, which one is in your kit, and you're going to be filling out the physical properties. You're going to be going through and testing it, and then and filling out what you test in those boxes, and then arrive at a conclusion for which feldspar of those 2 that I listed you believe it is. We'll go over more of that on Wednesday when hopefully some of you guys, a few more of you guys maybe get your rock kits in. Fingers crossed. And then at the very end of the data chart that you guys are going to be filling out, there is a space that says feldspar as well. And that's where you're going to write the physical characteristics, etc., for which of those 2 feldspars this one is not. So I gave you 2 options, and it is potassium feldspar or plagioclase feldspar. So depending on which one you think this is, if you think whichever one you think this in your kit is, you'll put that one up towards the top, and then the one that you ruled out, you'll write the physical characteristics for at the bottom. Excuse me. So these physical characteristics, let's go over the first one. There's a slide here dedicated to each of the main physical characteristics, and there's a column too in each of those slides for the different physical properties. First one we're going to talk about is crystal habit. Some people refer to this as crystal form or crystal shape. I am partial to the term crystal habit, and I feel like it's the one that I hear the most often talking amongst geologists. But in a lot of like 101 books, they will use the terms like form and shape. But I'm not a fan of those ones. So the slide there has lots of beautiful pictures of all these different shapes, right? There's this one that's kind of looks like a flower, right? There's another picture there where there's this golden cubes, right? There's also another sample there that has these purple kind of pyramids, right? there's another sample of this reddish kind of soccer ball, almost like-ish, kind of rounded crystal. There's another one at the bottom center that has these red hexagons that are kind of shaped like stop signs, right? But they're kind of like thick and chunky. Then there's also one other one, one last one on that slide that they almost look like windows. These kind of square windows, but they're beveled on the edges, on the corners. And they're a little bit thick. They kind of remind me of just windows, right? So those are all different minerals. And what I'm trying to draw your attention to on this slide are the different shapes that these crystals come in. It's the shape that that crystal is growing in. These crystals grew naturally in that shape, right? So a stereotypical mineral that a lot of people refer to, I don't think I actually have one that's just a quartz crystal, but let's go ahead and look at a extraordinarily smoky quartz. It's so smoky that it's just straight up black. So let's take a look at that guy. I think I may need to help get this in focus a little bit. So this is a piece of smoky quartz here. Maybe I don't need the clipboard. So this quartz, when it forms in crystals, it always forms, ignore the orange stuff for now, it always forms in a 6-sided prism. And if it is allowed to come to a point and what we call a termination, it'll have a 6-sided kind of pyramid termination at the top of it. And that's kind of the most common mineral, right? And it's the one that people draw an awful lot. So that's the crystal habit for quartz, where if it's going to grow uninhibited by other things, if there's stuff in the way, that can prevent the mineral from growing in its preferred shape. But if it's allowed to grow uninhibited quartz, it's going to form that really nice 6-sided prism terminated at the top with a 6-sided pyramid, right? Let's take a look at an example of fluorite. So fluorite, if you're looking at the slide there for crystal habit, it's that purple one in those purple pyramids. I happen to have a sample that looks like it. So here we can see these beautiful 4-sided pyramids, right? Hopefully you guys can see that. So these gorgeous 4-sided pyramids there, and it's what we call doubly terminated. So there's one on each side. You don't need to know the term doubly terminated, but you need to know the term crystal habit and know what crystal habit means. So these crystals were allowed to grow uninhibited. There wasn't anything like in the way of the surfaces that you see here. So they were able to grow in that preferred shape of the 4-sided pyramid, right? Down here though, let's take this sample a step further. Down here, this is also fluorite. It's just kind of greenish blue, kind of a really pretty turquoise color. And that wasn't allowed to grow in its preferred crystal habit. So it's just kind of this massive chunk, right? It didn't get to form those really pretty 4-sided pyramids. It eventually ran out of space growing, stuff like that, or it just wasn't conducive for it to grow in its shape. Then we have some geology puns going down in the, I love it. We also have right here some gypsum. So this is the same stuff that is in the crystal caves. It's just in a different crystal habit. There are limitations though to minerals. So some minerals can have multiple crystal habits, but we've documented the crystal habits that it can occur in. It's not like Gypsum can occur in whatever crystal habit it so desires, but there are a few different crystal habits that it can form into. And this is one of them, and I think it's super cool. So this is what's called a desert rose, made out of gypsum, because they kind of look like flowers a little bit. So let's see, just going over some other crystal habits. Let's take a look. This is one of my favorite lectures because we get to look at crystals. That's fun, right? So right here, my husband gave this to me. This is a corundum crystal, and you can see that it's this tall, six-sided prism, right? But it is not terminated. It's got a flat top. And my camera's not good enough, but if you were able to, if it was, you would be able to see that at the edge of these points that it comes to, they're actually kind of beveled at each of the edges, right? So, crystal shape, crystal form. It's the shape that a crystal will grow in, prefers to grow in if it's not inhibited by something else, causing it to be kind of more like this guy, you know, where it's like kind of massive. Let's see, there's another slide there that's also dedicated to a crystal habit. Different crystal shapes have different names. So, for example, halite, salt crystals, they grow in cubes, right? If you actually take your table salt at home and look at it under a magnifying glass, if you happen to have one, you will see that each one of those salt grains is an actual cube, right? And not only does it prefer to grow that way, but also if you break it, this is kind of getting ahead of myself, but if you break it, it'll keep forming like cubes. Diamond is also another mineral crystal habit name. So that would be for these fluorite crystals, these pyramids there. You would call that diamond. It is a diamond shape. It's shaped like a diamond, excuse me. So calcite, a mineral in your kit, it forms in these like rhombohedron shapes, usually, not always. Calcite has some really weird shapes that it comes in addition to that one. You can get things like a bladed or tabular, right? Crystal habits, or what we call like a dodecahedron. I love saying that word. It's kind of fun. Garnets come in dodecahedrons. And if you go back to the previous slide, the kind of rounded reddish crystal in the bottom left is a garnet. And that is showing that dodecahedron crystal habit. Let's go ahead and move on and talk about the next mineral property. These don't really go in any particular order, except for one that I put at the, that's the next one, but these don't really go in any, they really don't. They don't go in any particular order. But again, these are all the things you'll want to look for. So the next one on our slides, at least, is the next one. Luster. We talk about luster of minerals. What is luster? What does luster mean? Luster means the way that the mineral reflects light, or the quality of light that is reflected. I think that how it reflects light is kind of a bit of a better definition. What do I mean by that, though? It's an excellent question. Most mineralogy textbooks start out with just kind of two different qualifications for luster, right? And they start out with metallic versus non-metallic. So how does something reflect light? I have here a spoon, right? And I have here a canning jar. So we would say that this one is metallic and this one is glassy. Well, they're both shiny, right? They're definitely both shiny, but they're still different. This one, even though it's shiny, it doesn't look metallic like this guy does. The way that the light is being reflected off of these objects is different, causing them, while both to be shiny, just the luster to be different. And so when you look at an object, you can usually tell, like, is it metallic looking? It really reflects and really shines light back, or it's glassy. So glassy in this case, non-metallic though, more generally. There are a bunch of different lusters that minerals can have. See some other examples. So glassy is one such luster that a mineral can have. It can be metallic. Metallic is one. Glassy would be another one. So here I have two glass objects. One is colored, one's clear. So the way that the light is being reflected off of the glass is what we would call a glassy luster. It's not necessarily that it's clear or see-through. It's just how that light bounces off the surface of glass. And a lot of minerals will capture that, have that same reflection off of their surfaces, right? Another luster that we talk about in geology, some minerals have a waxy luster. And when we say waxy luster, we literally mean that it looks kind of waxy. If you grab in your kits, if you happen to have those, sample number 17. If you have the larger kit like myself, it's sample number 19. This mineral is talc, and it's a very soft mineral. It feels kind of greasy or waxy. And when you look at it, you might see some areas of it that also look kind of waxy. And that's not your eyes. And that's actually just the way the mineral looks. Is it typically has kind of a waxy look to it. So some other mineral lusters we can go over are pearly, like pearlescence kind of minerals. So this is a pearl necklace. A dear friend of mine in high school gave this to me. She was from Korea, and in Korea and parts of China and other parts of Asia, pearls are not rare, and nor are they valuable. So they're pretty cheap in other countries. You can you can see the way, hopefully, maybe if you have something that's kind of pearly at home, you can look at it and see the way that the light reflects off of it. And that we would call like a pearly luster, right? I have here also like a pearl inlay box from the same friend. And you can kind of see, and in these instances, sometimes the pearl has like different colors to it as well. Right. And then I have one other kind of pearly sample to show you. So this is a fossil. Modern shells, though, that haven't been fossilized will still show this. Right here, you can see this little rainbow there. That's the pearly luster that we're talking about. Just the way that that kind of reflects light back at you. Call that pearly. So let's go over a few more lusters types. Oh, hey, here's another metallic one, another metallic mineral. This is pyrite. This is fool's gold, right? Yeah. Another mineral luster that you guys will probably encounter is dull or earthy. Like, what the heck? Dull or earthy? So with like earthy, it just means that it is this really dull, doesn't really reflect light back much, right? It's just this earthy color. It doesn't mean brown, right? Because I have another brown mineral here, but it reflects light. Got some you know, maybe glassy or resinous. Other words, vitreous. Don't worry about that one. It's different though. This one is so dull by comparison. It doesn't really reflect light back. I hope to photograph this sample for you guys and post it on Canvas because I realized earlier today that the crystals are probably going to be too small to see. They're tiny. I found this one with a buddy of mine in the field, and this mineral here is a black mineral, and it actually it's not glassy, it's not shiny. There are distinct crystals on it that are in kind of it's hard to see, but they're in kind of, I think, a more bladed habit, crystal habit, but they're not shiny crystals. Like, they're just not shiny. They're dull. They're earthy in luster. I'll try one more time, but this camera is just not great. So I'll try to post some pictures of that online. Another luster that we can talk about is resinous. If any of you guys have some jewelry or maybe some other objects or knickknacks that are made out of resin, the way that resin reflects light is definitely different than the way that glass reflects light. So you can typically tell by looking at something that it's made out of resin instead of glass. And we call that look resinous, right? Resin can be different colors, but you can still tell just based off of the way that it's reflecting light that it's resin. I actually have some opaque black resin. I don't know how well this is going to show up in the thing here. So in the center of this ring that I got from Hot Topic, there is black resin. And the way that that reflects light, it's not showing up super well on the laptop's camera. But if you were to compare the two and you were able to see this better, you would see that the way that that resin reflects light is different than the way that this glass jar reflects light. Another crystal texture is fibrous. Crystal luster, excuse me. Another crystal luster is fibrous. So if you're looking at that slide 11, the top mineral in the top corner is kind of this silky, fibrous looking like texture, right? So minerals can actually appear fibrous, and sometimes those fibers are really soft. For example, asbestos. I didn't put a sample of asbestos in the slides there. And asbestos, by the way, tisk, I really shouldn't be using that term. Asbestos is not a mineral name. It is a family of minerals. Again, same thing with garnet. There's no such mineral called garnet. That's just the name of a family, an umbrella term. But the different varieties of asbestos are like really, like, especially the bad ones, they really look like fibers, like clothing fibers, right? It's crazy. And they're pretty soft when you touch them, I think. Some of them, though, are a lot harder. So by fibrous, I almost brought like a scarf to kind of show you the edges, the fringe of the scarf to show you what fibrous means, but I thought it would be a lot more fun if I used my rainbow llama alpaca plushie, Jerry, who I won at an arcade through one of those claw machine things. So what we're looking at here are the fibers, right? This is fibrous. That's what we're talking about when we say fibrous. And you can kind of see how that crystal on slide 11 has that similar fibrous look to it, right? Let's take a look at one more fibrous mineral. This is tiger's eye. So you can kind of see those individual lineations in here. And that is kind of the fibrous look that this guy has. However, these are really hard fibers. And the fact that it grows in those really small, like needle-like fibers is why it shines kind of the way that it does, right? So if you have any tiger's eye jewelry, you can pull that out and be like, oh, hey, look, fibrous. I do actually have, I don't know how well this will show up, but this fluorite sample does actually have a really fibrous, probably zeolite mineral on it. Let's see if we can get it to show up on the camera. Cross your fingers. So this white stuff here in between the two colors of fluorite is a zeolite mineral of some sort that has a fibrous texture. And it really looks like hair, you know, when you look at it, and it looks fuzzy. But they are hard. But they look fuzzy, like the, you know, llama, alpaca fur on my stuffed animal. See, any other lusters that I want to go over? Nah, I think we're good. We hit a bunch of them. Looking at that slide, though, I will go over just what you're seeing there. So on slide 11, mineral properties luster. In the bottom left, there's a mineral there. I don't know which one, but it has a metallic luster. The top right one has a fibrous texture. In the next row down, there's two minerals, a black one and a green one. That black one is displaying an earthy luster. It's not really shiny. It's very dull. And then next to it, that green mineral there, serpentinite, that one has a kind of greasy or waxy luster to it. It's kind of hard to tell in there, and I wish that we could pass around samples for you guys to like look at and reflect the light off of. But it's got that waxy kind of look to it. In the bottom row there, on the right-hand side, it's kind of the center picture in the bottom. That is a diamond, a uncut diamond, and its luster is so clear, right, that we call that luster adamantine. Next to it is a quartz crystal, and we would call that luster glassy. It's not quite as pristine and clear as this adamantine diamond that's next to it. So those are some really good example pictures of the different lusters. And different minerals are gonna have different lusters. And it's one of the things that when I am presented with a mineral that I don't know what it is, that I look for to figure out what it is. And yes, I do this a lot. Our college actually has a gigantic rock and mineral collection that was largely donated over the years, and nobody documented what they were. And they put them into boxes, transported them to the college, and didn't open those boxes for like 20 years. And when they hired me, they said, hey, we have a bunch of boxes. I'm also a lab technician in addition to an associate faculty. And they were like, hey, we have a ton of boxes here, as in like an entire room filled, like small room filled with boxes that of rocks and minerals that need identifying. Would you be willing to take on that project? And I was like, heck yes, I love looking at minerals. I could do this all day. And then you get to it and you realize how tedious it is to test every single one of those samples. And you find a lot of weird things and you're like, I don't know what this is. But in doing that process, I was looking for luster and crystal habit, right? And the next properties that we are going to talk about, color. This is the most misleading mineral property that there is. Oh, color, you are insidious, you are devious, and I hate you and love you. So there's a ton of pictures on this slide, slide 12. There's green crystals, there's clear crystals, there's blue and black and purple, brown, red, pink, in kind of this orangey color, and it's all the same mineral. They are all quartz crystals. Yeah, some minerals, not all minerals, some minerals come in like every color under the sun. And you'll be filling that out on your charts. So when you go to look up these minerals, using whatever search engine your heart desires, whether it be cosia.org because you like planting trees, or DuckDuckGo because you like your privacy, or google.com. It's got a really nice, robust search engine. You'll find, and you'll look up these various minerals, and you'll see that some of them come in a ton of colors. Some of them only come in like 1 or 2 colors, or maybe even only like 1 color. Quartz is one of those fun ones, though. It comes in every single gosh darn color. However, with quartz, I can usually tell that it's quartz based on its luster, as well as some of the other properties that we're going to be going over in just a minute. So let's go ahead and look at some other minerals that are the same color, or different colors, but they're the same mineral. So let's come back to my smoky quartz friend here. And now we are going to look at the orange things on here. Any guesses as to what that mineral might be? It's a very orange. And I wish you guys could like see it in person, because you would see that these crystals are inexcusably orange. So any guesses? It's garnet. So these minerals on here, these gorgeous orange crystals, are garnet. And you're like, hey, wait a second. Like, I saw a garnet like a few slides back, and it was like this really pretty, gorgeous, reddish kind of color. This kind of wine red color. Yeah, it was. And this one is a different garnet, and it comes in the color orange. I also have this mineral here. Let's see if we can get that to focus maybe a little bit better. Focus is okay. It's about as good as it's gonna get for this webcam. So, any guesses? This mineral is, if you guessed garnet, a garnet mineral, you would be correct. My husband has a game that he plays with me. I freaking love this. For like my birthday or Christmas, he'll get me a mineral sample. And he doesn't tell me what it is. He gives me these things, and it's my job to identify the mineral sample. And usually I get it like pretty quickly, but sometimes he stumps me, and I swear I'm pretty sure he says he just goes based off of ones that he likes, but he also relishes when that mineral sample happens to stump me, and it's like he'll go for like the oddball ones. For example, this garnet stumped me for a few days. Why? Why did it stump me for a few days? Because of its color. I was judging this mineral based on its color in part. That was one of the things that kept me from identifying this mineral right away, because I'm not used to seeing garnets in this color. But garnets come in all sorts of colors. The other thing that stumped me was the fact that this is only half of the crystal. This is the backside. It's all broken off. So only some of the crystal faces are present. And I was mistaking this for a different crystal habit because I wasn't paying close enough attention. And then 2 days later, I was paying close enough attention, and I was like, oh my gosh, this is half of a garnet. It was so tiny. It's such a small crystal. I would hate to conduct like other tests on it that would end up damaging the crystal. So like hardness and streak and other tests, I just couldn't bring myself to use to identify it. So detail is key. Detail is key. Let's see. Crystal color, I think. That might be, I have some other samples here that I could show you with crystal color maybe. Calcite. Calcite normally comes in this color, kind of this clear whitish color, but that's not all it comes in. It also comes in a wide variety of colors. This sample here is also calcite, and it's got some purple areas and some stained with iron oxide areas, right? And if we look at the back, it's got some more reddish wine kind of colors at the base of those purple terminations, right? And this area here is kind of a clearish, almost tealish area, right? This wacky looking, you know, pine cone like hedgehog like sample is actually also calcite in just another weird crystal habit. This is called a dog tooth crystal habit. You don't need to know that, but I have fun with this stuff. And it's like this brown color, right? So yeah, definitely something to keep an eye out for. This is rose quartz. It's not showing up very rosy here. I promise in real life it looks more pink than that. Purple quartz, amethyst. Amethyst is just purple quartz. Sorry, amethyst, you're not that special. You're just purple quartz. And then again, smoky quartz, right? Comes in all kinds of colors. So when you get a mineral, the last thing you should look at when identifying it is color. But that's so hard because it's like the first thing you see, right? Resist the urge, resist the temptation to look at color. Color should be more of like a confirmation rather than one of the things that you're looking for. And it's so hard to do, and we all make this mistake. Try not to do it though. Try your best. So let's look at the next slide with the next mineral property, which is hardness. What do I mean when I say hardness? When I say hardness, what I mean is its resistance to scratching. I don't mean its tenacity. Tenacity means like its resistance to shattering. It's a different mineral property that we won't cover, but there you have the definition for it. But hardness is resistance to a scratch on the surface of the object. So different minerals have different hardnesses. Some of them are really, really soft. They're so soft, for example, in the case of graphite, it takes barely any pressure at all to just to scratch its surface. And you scratch it across your paper and the whole thing comes apart, right? All across your paper. If you were to take your fingernail onto this graphite pencil here, you would find that you would be able to scratch it with your fingernail. Let's go back to another mineral sample in your kit, which is talc, right? This guy. So if you happen to have that in hand, go ahead and find one of those really waxy spots on the sample, right? And take your fingernail and just dig it into that sample, right? And you will find, I don't know if you can see a little bit of powder on the edge of my fingernail there, but you will find, here's where I scratched it. You can scratch it with your fingernail. It's not very hard. If you take a sample like sample number 1 and scratch your fingernail across it, you will damage your fingernail because this is harder than your fingernail. So that's a very characteristic feature that we use to help us identify a mineral. Why did I ask you to grab glass for this lecture? Not just so that you can see the glassy luster thing, but also we use glass. We'll do this on Wednesday with our samples, but you can use glass to scratch this because and see how hard it is compared to glass. Glass has a known hardness, right? And so do your fingernails. Your fingernails have a known hardness. Pennies that are actual copper pennies, we're not talking about anything made in 1983, between now and 1983, but 1982 or older pennies, actual copper pennies, have a hardness of 3.5. They're never 3. They're never like, 4. It's always 3.5. Glass has that hardness of, I don't have it memorized, I should, 5.5. And your fingernail is 2.5. So your fingernail is also pretty soft. And you've probably noticed, you may have noticed this throughout your life, that your fingernails can get scratched fairly easily. So the fact that this talc sample is able to be scratched by my fingernail means it is extremely soft. So hardness, again, there, something that we test. Some minerals have a range of hardness where it might be 3.5 to 4. However, some minerals do have a specific hardness. It is always that hard. It is always that resistant to scratching. We use those minerals as index minerals, and they're really helpful because if you have those on hand, you can use it to test other mystery minerals, right? And figure out and narrow down their hardness. I have a mineral testing kit for hardness in my office for when I go through the collection, and it has a bunch of index minerals in it, and I scratch them against each other to try and figure out, narrow down the hardness of the mineral. Let's also, I was using some numbers, but I realized that I kind of put the cart before the horse there. Sorry. I threw out some numbers of how hard things are. What I was referring to is the Mohs hardness scale. And on slide 13, you'll see that there's this scale. It goes from 1 to 10. And Mohs is the name, I believe, of the dude who made this hardness scale. Don't quote me on that. I should really look that up. Mohs hardness scale, talc being of a hardness of 1, diamond being a hardness of 10. So relative resistance to scratching. The mineral that has the highest resistance to scratching, it is really hard to scratch, be a diamond. That's why they get used in jewelry a lot, is because it's so difficult to scratch the object. In fact, they use other diamonds when they need to cut a diamond or polish a diamond or scratch a diamond. You can only scratch a diamond with something that is equally hard, a diamond. And so it's just that 1 to 10 relative scale that's used to tell how hard your mineral is. You'll also see kind of some example images there of someone scratching what's probably some talc with their fingernail, or scratching some quartz against some glass. Quartz is harder than glass, so it is able to scratch the glass instead of the glass scratching it. The crystal is going to be undamaged if you scrape it across that glass, and it's harder than glass. And then there's also a diamond anvil at the bottom of it, showing diamonds polishing diamonds. Let's go ahead and move on to the next slide, which is cleavage or fracture. So what do I mean when I say that? What I mean is the way that the mineral cleaves, right? So if you do break the mineral and it breaks along a plane of weakness, does it break along a plane of weakness, number one? If it doesn't break along a plane of weakness and it's just all irregular, we would call that fracture, and we would say that it does not have any cleavage. It doesn't have a plane along which it cleaves. So I'll avoid looking at this sample. No, I'll look at some of the samples now because I think most of you guys have your rock kits, but we'll go over each of the samples on Wednesday. So go ahead and grab your sample of calcite, which is, it should be sample number 5, unless you have one of the big rock kits, and then it's sample number 6. It's in that kind of rhombohedron shape, right? This guy here, I've got a slightly bigger one that I'm going to use because it'll be easier to see on the webcam. So there is a plane right here, right? And when I shine the light, see if I can get it coming through my window just right, you can see that there's a pretty flat plane that reflects light and shines it right back at you. That is the plane along which this sample cleaved when someone broke it. Yes, when you break this thing, it literally just breaks into smaller rhombuses, right? Rhombohedrons. Same thing like with salt. When you break salt, it just breaks into smaller cubes. And the surfaces of those cubes are like super flat. It is a legit just straight across plane that it broke along. Looking at let's look at your biotite sample. What did I do with my biotite sample? Sample number 4, or if you have the large kit, sample number 5. This top surface here is a cleavage plane. When someone broke this sample, it literally broke in a sheet and created that very flat surface that you're seeing there. And it's literally just, that is so perfect, right? It's not irregular or conchoidal at all. Conchoidal is another word that you'll want to know because you'll be seeing that a lot when you look up these mineral samples. Go back to slide 14, if you will. And on the top right-hand side, there's this clear quartz crystal there. And if you can kind of see on the right side of it, there's this kind of like scooped out shape from the crystal. Kind of looks like maybe the interior of like a shell or something of like a clam, where it's this kind of scooped out shape. It's kind of got that little round thing to it as well. That is called conchoidal fracture. And you see that in minerals that just don't have cleavage planes. When you break it, it doesn't break along like a nice cleavage plane. We should talk about why these minerals do or do not break in these kind of cleavage planes or not. It has to do with the molecular structure of these minerals. So the ways in which these, like the bonds of the different elements, right? So looking at the bottom left corner of slide 14, what that's depicting is a picture of mica on a molecular level. So one of these guys, right, in your kits. And there's a plane of weakness along this edge right here, going lengthwise with it. And it's just really easier for the mineral to break along that plane than it is along other planes. If you're not careful with your sample, like me, you'll see that you can actually break it along that cleavage plane right like that. Broke that off right there. And it just cleaved perfectly right along that cleavage plane. So you can literally just take a knife blade or your fingernail and cleave it off. So plane of weakness, cleavage. Now, some minerals have multiple cleavage planes. Some only have one, you know, in the case of quartz, has none. So this guy here has 4 cleavage planes, right? I believe 4. So it's got one right here, or it has 3. So it's got one here, and one here on the top, right? Whereas this guy here has only one cleavage plane. It's just straight across. So that's also something that I look for is, does it have cleavage? Number one. How many cleavage surfaces are there? And then not only that, but I also look at the angles of those cleavage surfaces relative to one another. So this gorgeous calcite crystal here, it's not really that gorgeous. It's not that special. If we notice, this isn't a 90-degree angle. It's not a perfect 90-degree angle. It's kind of it's a rhombus right there, what we're looking at. And it's like that on all sides too of the crystal. Whereas if I were to look at a salt crystal, they would all be 90-degree angles, right? And those angles help me also determine whether it's like a calcite crystal or if it is like a salt crystal or something like that. When I was identifying this sample, I did not look for cleavage planes, and I should have, because if I had, I would have been able to identify it a lot quicker. This is a cleavage plane right here. And this is another cleavage plane right there. And they are at a specific angle to each other, right? That should have tipped me off to this being calcite. But I was not paying attention. It's a bad geologist. Should be paying more attention, right? When I'm trying to identify these things. So that's pretty much covers cleavage. Let's go ahead and talk about streak, the mineral property streak. So streak refers to what color a mineral is when you powder it. So, and we have an easy way of powdering this in geology. We take a small matte porcelain plate. This one is white because it's easier to see dark colored streaks and kind of tell what color that powder is. And so here I'll take my fool's gold, my pyrite, and what I will do, it's much better if you set this on a table and then do that, the streak. You got to give it some elbow grease, by the way. You really got to, scrape it against that plate like you mean it. And that's why you want it to be on like a table rather than in your hand, because you could break this and cut your hand. Likewise, if you have a glass plate and you're trying to scratch it, in both cases, you need to scrape that thing against the other object like you mean it. Don't break it in your hand. So I'm going to put this on the table and scrape this mineral across it. Hopefully you guys can hear me wailing on this streak plate. And it has a really dark, almost black streak. There's a little bit of that kind of goldish shine to it, but barely. It's mostly like a black, dark gray. However, if I take, let's say this crystal right here, see if I can find, here's a corner that I don't care about. It's just the fracture of the bottom of it. It's not pretty to look at, so I'm not ruining anything. I'm going to take this bottom surface here and scrape it against this plate. Spoiler alert, you won't be able to see it. Maybe if I kind of shade it, you can see the powder. Probably not. Oh, you can almost see it where my fingernail is kind of pointing. Nah, maybe it's my imagination. It's just a white powder. Isn't that crazy though? Because the mineral is black. Like what I'm, are you seeing what I'm seeing? This is black. But when I powder it and I scrape it against the streak plate, it's just a white powder. So crazy, right? Quartz, no matter what color it is, if you powder it, it's going to be this kind of like clear whitish color, the powder. Pyrite, if you do the same, it's going to be kind of more of like a black, dark gray, maybe with a little bit of gold hints to it. Copper, go ahead and look at your copper there. I'm going to scrape this against the streak plate again. You know what? I really don't want to do this with my native copper. It's just too pretty. And I have a copper penny on hand. I'm going to do it with a copper penny. If you happen to have a streak plate because you are a geology enthusiast and you're doing this with your penny, you're going to want to rub it on there for a little bit longer because your penny has some tarnish on it. And we're not trying to look at the tarnish. You want to get the streak of a fresh surface on there. Defacing currency. Sorry, America. Sorry, US Treasury. Don't come for me. It's just a penny. We can see that it's got a brownish and it'll have a metallic coppery look to it. So that's an example of where the color is actually reflected in the streak. And it's always going to be that color. Streak is definitely really helpful in that no matter what color your mineral is, it's always going to have the same streak color when you powder it. However, streak becomes unhelpful in that most minerals are silicate minerals. A lot of them are silicate minerals, and they all have the same white streak. All the silicate minerals have like a white streak. And you're just like, great, thanks. Silicate family, why you gotta be like that? Whereas if you go into like the sulfide category of minerals, they have different colors and things, but no, the silicates just gotta be like that. So yeah, on slide 15, you can see a bunch of different minerals there. They've got different color streaks. One of them is like a brown color. One of them's like a reddish color, and one of them's kind of this metallic-y gray. And then there's like one streak plate at the end of that row of several minerals. And you're just like, did you even do anything? It just has a white powder on it. You can't see it because limitations of cameras and things. Right? It's there. They did do something to it. Let's go ahead and move on to the next slide. So there are some additional mineral properties. I think I forgot to include this on the slide. Hooray for you guys. It's other, or not on the slide, but on the lab. They are other identifying mineral properties. So I'll have you guys, I'll need to like add that though, because it's really important. It's super important. There are these other additional properties that can help you identify minerals. So magnetism, super important, especially when you're trying to tell like hematite apart from magnetite, because they look really similar and have very similar properties. But it makes it super easy because one of them, magnetite, you guessed it, is magnetic. And hematite isn't. So some minerals are magnetic, right? Effervescence is the next word on that slide. What the heck does effervescence mean? Let's see if I can demo it for you guys. So you're going to need some HCl, hydrochloric acid. It's stomach acid. I think they also use it to clean pools too. Take my calcite crystal here. Hydrochloric acid will react with calcite. So if I pour this onto here, so you got a little bit on that corner there. You can't really see it. What a bummer. I'll put another drop on here. Oh, drip some hydrochloric acid on my laptop. It's fine. It'll be fine. It's fine. So when you put hydrochloric acid on here, what I was hoping you guys could see, but I don't think you can. One more try I'll do. Is that it bubbles and it fizzes. Let's try this. No, sorry. Bummer. You could kind of see it maybe. Yeah, if maybe there's probably like a much higher definition like video clip on YouTube, but it bubbles and there's a chemical reaction going on between the hydrochloric acid and the calcite, and that creates this effervescence. And calcite's not the only mineral that does that. For example, malachite, that really pretty green mineral that's used in jewelry sometimes, if you powder it, it will effervesce, but only when you powder it, not when it's in its like really pretty crystal format. So that's really helpful for me when it effervesces. And honestly, when I am trying to like identify stuff, I try to tell students in my classes, like in labs, if you have hydrochloric acid and you test your mineral and it fizzes, thank God, because there's only like a smaller handful of minerals that do this. And that is so helpful, because then you've only got like a narrow list of minerals to choose from, and you can use other identifying properties in tandem with that to help you figure out which one it is, right? So let's go ahead and look at the next property on there. Which one is it? Smell. Yes, some minerals actually have a smell. Sulfur being one of the like most noteworthy ones. It has a very pungent smell. And yeah, so some minerals do have scents to them that help you identify them. And then another one is feel. So the way that a mineral feels when you touch it can also help you identify it. So going back to our sample talc in the kits, when you like rub your hand on it like this, it feels kind of like waxy or greasy. And you kind of go like, ew, ew, when you do that. And it's waxy, it's greasy, that's weird. And that is actually very characteristic of the mineral talc. And by that kind of greasy, waxy feel, that is one of the characteristics that we look for to identify it. So yeah, feel is the way that something feels in your hands. It's also a very helpful identifying property. So with that, let's end today's lecture. And next time on Wednesday, we'll pick up talking about gemstones. Yay, my least favorite term. And we'll also talk about conflict minerals briefly. And we will go over the stuff in your rock kits. So we went over a little bit today because we had our scientific method chat. And I love showing you guys like tons and tons of samples because it's my favorite thing to do. I love looking at crystals. If you have any questions, go ahead and throw them in the chat. If you want to do like a Zoom Q&A, go ahead and throw your email in the chat, and I will say whether you prefer Zoom or Google Hangouts. Google Hangouts for me is kind of easier, but because I just send you like a quick email and it should show up in your email account that you received like an invite to join. And it's just a little bit simpler software. Google Hangouts. Not as many buttons to get lost in. So let's see. Are there any other announcements I should do before the 11 of you who are watching leave? I also am going to add a column to those lab, to the lab. I just posted that this morning, like right before noon. So if you already downloaded it, you'll need to re-download it again. I apologize for that, that slipped my mind, but I'm going to add a column for other identifying properties on your labs. Let's see, I think that's everything that I have for you guys for today, though. So I will see you guys on Monday. Yeah, bring your rock kits. keep the glass on hand, right? As well as the copper penny and the graphite. And yeah, we'll see you then.